Welcome to my presentation, which is about time series analysis in healthcare, especially arrhythmia detection in ECG signals. My name is Aaron Horvath. I'm a data scientist working at Unit 8, which is a Swiss technical consulting company working with big data and AI. As part of this presentation, I'm going to talk about the followings: time series analysis in healthcare, anomaly detection. Then I'm going to introduce ECG signal. What do I mean about what's the definition of arrhythmia? Then we're going to talk about DARTS, which is an open source library, which we're going to later on use to develop anomaly detection models for EKG arrhythmia. And then I'm going to provide a summary of our overview we did, and then some few concluding remarks. So, about time series analysis in healthcare. Time series is basically everywhere in healthcare, starting even by basic resource allocation. For example, one may want to predict how many patients are going to show up for a certain window or at the ward of a hospital, and with respect how you need to organize your staff's nurse presence. Next to that, second obvious focus point is diagnostic, when based on the historical data of the patients, using AI, potentially one can leverage and extract actionable insights which could be turned into improved healthcare and provide better patient outcomes. Someone doesn't think about it, but it could be a quite interesting topic, is predictive maintenance. A lot of devices and its emerging number of devices being deployed and used on a daily basis in the hospital and in the healthcare space, and obviously this has also a lifetime. Just thinking of a heart pump, even if they have a fault tolerance built in with a second circulating system, it would be quite good to know when the system or a pump system fails and potentially impacts and harms the patient's life. If we want to, basically we can define the following time series analysis methods in healthcare in these 5 following categories. One would be anomaly detection, where we want to try to identify rare events or observations which usually deviate from a normal expected behavior. In this case, later on we're going to see how arrhythmia deviates in case of an ECG signal. In addition, as the next following topic could be classification, when we are interested to know what time series data points are belonging to each other. For example, in the COVID-19 pandemic, we could see that whenever the hospital was overwhelmed by a number of patients and they had to create a triage process, which patients are going to be treated, they had to prioritize the patients. Based on the historical course of the evolution of the disease or sickness, they could potentially predict the outcome and seriousity level, and they could define how serious certain patients and which patients could be potentially being sent home and which should stay in the hospital. Obviously, if we don't know previously what labels or information we are looking for, we could use unsupervised learning approach, clustering this time series data and potentially identify these risk groups. Obviously, then we could do the forecasting. Once we know that we can develop forecasting models when we can predict the patient outcome, even in a very standard personalized manner. And then as a 5th pillar, we can look at motif discovery. As an example would be potentially diabetic patients, certain glucose spikes in the measurement eventually does not carry a certain anomalies, which would be also an interesting topic to cover, but potentially an underlying pathologies which could be pathologies which we would identify through this analysis. So when just going to focus on the first point, anomaly detection, let's define what is anomaly at first. So anomaly is basically can be different in length and types in terms of amplitude, frequency with respect to the underlying data in mean or trend. It's definitely something which is not expected behavior. If we want to subcategorize this, then we can say that we're going to talk about point anomalies, like a patient temperature spikes when in an in-hospital care. When we talk about collective anomalies, we can think of it when the heartbeat becomes irregular, although we are expecting that there is a heartbeat. And the contextual anomaly would be when a diabetic patient, for example, receiving insulin, and they're still receiving after a decaying glucose bloodstream level, they are still occurring a certain plateau, which would be a contextual anomaly. If you need to approach the anomaly detection from the machine learning point of view and the three key pillars like supervised, semi-supervised, or unsupervised learning, we can see the differences and define the differences, how they look like. When we talk about supervised learning, we understand that we need to be able to provide labels with respect to the anomalies, and the models as a consequently gonna learn to distinguish between those patterns of the signal which are non-anomalies and which are anomalies thanks to the labels. Semi-supervised learning is using a principle to show as part of the training data to the model only non-anomalous samples. So basically the model learns to categorize non-anomalous behavior, and because of that it's going to be able to identify anomalies and flag them if they occur. The unsupervised learning do not assume anything with respect to the training data, which contains both non-anomalous or anomalous values without any labels. However, the model potentially is still able to identify the anomalous behavior based on the assumption that anomalous subsequences within a time series occurs quite rarely. If you want to approach how costly to potentially develop a machine learning model in any categories, so how much effort we need to put in, we want to see that for the labeling, especially any kind of long time series which requires human effort, is very expensive, and even beyond that, it also becomes quite limited with respect to which anomalies it can be recognized, because the models developed on label data won't be potentially able to generalize for those anomalies which, as part of a label, we haven't shown to the model. On the other hand, the semi-supervised, unsupervised modeling becoming the quite preferred way when it comes to anomaly detection models, and there is very minimal effort required to make sure that certain underlying time series characteristics as part of the training data there, and because of that they are very popular. So, as part of the next point, let's talk about ECG signal. So ECG stands for electrocardiogram, which can be considered the simplest and fastest test used to evaluate the heart. It's basically attaching to the skin certain electrodes which are measuring the depolarization and polarization of the heart. As we see on the right hand side, we see a heart which are pumping, and due to this depolarization and polarization manner generates a spike-like measurable signal, which is composed of quite key characteristic features. So the P wave stands for when the atria is depolarizing, the QS complex when the ventricular depolarization, when the basically ventricular is pumping the contracting, and followed by a T wave, and basically that's a single unit of one heartbeat. Anomaly occurs, which we're gonna call in this case arrhythmia, an irregular heartbeat, when the frequency, the rate is off. As we've seen in this demonstration, the first few peaks followed in a quite regular manner, and after the fourth one, then there is an arrhythmia, which is mostly presented that this QRS complex has a premature spike followed by a delayed secondary spike. So, and this is the anomalies we've tried to capture in the upcoming exercise and develop a model for it. But before that, let's talk about the tool we're gonna use for it. So, DARTS is an open source Python library which is designed for time series manipulation forecasting and anomaly detection. Its core component is a time series class, which is immutable and allows us the basic unit to manipulate in time series. It supports the scikit-learn specific fit predict interface. It has an abundant number of classical and state-of-the-art machine learning models used for forecasting, and it has a very simplistic, user-friendly, intuitive API, so the onboarding and start with the tool is very simple. So just to recap again, so the basic unit of DART is a time series object, which is basically captures the time, how it looks like on one axis, and the secondary axis, as if you want to think of columns, the first column would be then basically the time, the second column, in case of a union, there would be an actual signal. If you have multiple signals, then we have a chance to talk about multivariate time series. And also the object allows us to combine multiple samples and eventually use them as a signal as either deterministic or any kind of probabilistic information about even as a standard deviation around a certain signal, and so on and so on. So basically, in one basic object, we can keep all of this information together and is a parallel manner containing them as the samples. So instantiating the time series is very simple, and using a factory method. Basically, from a single CSV, a pandas table, an X-ray, one can instantiate the time series object, and the underlying data, usually one column containing the time information and other the corresponding signals, and one with a simple flag can indicate which column is actually containing the time information. And then as part of it right away, we have a chance to understand how many channels we have, and with a simple plot we can even visualize and create this figure right away. This time series object also supports a lot of methods and arithmetic operations what one would like to use, like shifting, scaling, and to demonstrate next to these arithmetic operations, we also have a data processing module which allows to use transformers, do imputation of missing values or windowing. And this is a comparison, the manual shift and scaling I did. We also could achieve just using a scalar. For visualization reason, I shifted it with 2 data points, but otherwise it's a 2 signal. As part of the forecasting models, DARTS is huge collections, and all models support univariate forecasting and all sharing the same Frit predict API, similarly to scikit-learn. On the right hand side, we see the first 8 out of the 30 plus forecasting models currently available in DARTS, with the corresponding features they support. Beside the univariate forecasting, standing for one column or one data series information, other models potentially support multivariate forecasting or even training on multiple series at the same time. Certain models allow us to use covariates, which is not necessarily part of the input data, but would be interesting to incorporate it as an additional external information. There are certain models are offering probabilistic forecasting, and the library also provides the neural network related features such as early stopping and other monitoring opportunities. Next to the forecasting models, we recently extended DARTS with another anomaly detection module, which has 4 subcomponents. One are the scorers, which are using the time series information to score it and derive an anomaly score from it. There are detectors, which are basically binarizing this anomaly score into 0, 1, indicating where the anomaly is occurred. There are certain aggregators, when in case of multiple binary predictions combines it. And then there is anomaly models, which are basically combine the forecasting or filtering model with the scorer, taking a time series and using the scorer afterwards generating anomaly score. We're going to later on how an anomaly model with these 2 components can be created. After this introduction to DARTS, we can look at how we can detect anomalies in ECG signals. So the goal is that we have a raw data, such ECG signal like on the left hand side, and after anomaly detection, we are going to be able to flag where the arrhythmia is actually occurred in the signal. So we're going to apply the following rule. We're going to develop an anomaly model, which is basically going to be trained. We're going to train a forecasting model on the training datasets which are anomaly free. Because of it, it's going to allow to generate and forecast time series data which are also anomaly free with respect to the future. However, if the data contains an anomaly as a frequency shift, this can be captured by a scorer by basically comparing these 2 signals and deriving a certain anomaly score, a different score between the actual and actually the anticipated forecasted time series data. And this anomaly score using a detector can be binarized later on. So as part of this exercise, we're going to use an open source available and already curated dataset. Basically, thanks to that, it's already curated and is basically created in a CSV format containing the time series information, the 1 channel ECG, the 2nd channel of the ECG, and even the known anomalies. Basically, using the same interface, we can instantiate a time series object by loading the CSV file, indicating which column basically contains the time information, and then we can even use and indicate them and split them out different components of the time series containing the ECG and the anomalies. And with the simple visualization that's been seen before plot, we can actually visualize all components. And this is the overall first 1 minute 20 seconds of the signal. In order to develop a proper anomaly detection model, we would like to understand the signal and do a little bit of analysis on it. And we know that ECG signal is a quite periodic signal, and one of the key components is this one single heartbeat unit, what we have seen before. So to support the detection of this one single unit and potential deviation from it, we would like to understand what is this one single unit and what is the frequency of this single unit. To do so, we can use an autocorrelation with its own signal, and then as part of this, we can automatically, with these two lines of code, generate the signal, being the most dominant peak around 130 data points apart. And by knowing that the frequency used to measure or record this ECG signal is 128 Hz, from which we can calculate that this patient had roughly a 98 pulse over the course of recording. So once we know what is the time span required for one single heartbeat, then we can create a train test plate for developing the anomaly detection model. So just by visualizing, here we can see that in the training data set we do not have any anomaly. On the other hand, in the test set we're going to have one anomaly, and we hope that the trained anomaly detection model is going to be able to identify it. In Darts, the definition of an anomaly detection model is very simple. It's basically composed of a forecasting model and one or more scorers. In our exercise, we're going to use a linear regression model instantiated with a certain lags identified as part of the analysis. This period, this 130 data points between this one heartbeat. And as scorers, we're going to use norm scorers, which is basically, it's a very simple scorer point-wise comparing the forecasted and the actual time series data. And we're going to use a k-mean scorer, which you're going to later on introduce how it functions. As the ECG signal we have two channels and both carry the same information, we can leverage it and we can instantiate our k-mean scorer in the parameter component-wise false, which means that instead of treating the two separate channels as two time series and assign an anomaly score to it, we are able to combine by windowing the signal, taking the two time series, windowing it, and then combining the corresponding windows next to each other, concatenating them into a simple vector, and applying the anomaly score on them. Because of the two signals within the same window contains the same information, we can potentially improve the signal to noise ratio. Once we instantiated the anomaly model, we can train it by using the fit method and assigning the training dataset. In case of an anomaly model, we don't use the .predict method. We use the .score to right away to do the forecasting next to the provided test dataset, and then use every score assigned as part of the anomaly model to generate anomaly scores. To illustrate how well the linear regression model is able to predict, on the right hand side we see the test and the predicted dataset with the on purpose injected shift for visualization purposes. To evaluate how well we forecast is also very simple. From DARS we can just import certain metrics like mean absolute error or root mean square error, and then with a very simple liner we can evaluate how well the model performs. So the k-mean scorer is basically taking the training data set, basically slice it up into windows, and to the windows basically fits a k-mean clusters. And because of it, we are fitting on this data set, the cluster is going to be assigned in a way that each vector is going to be a quite slow distance from the closest cluster. However, if we try to basically assign an anomalous window to one of the clusters, because it was not part of the training, it's going to be a significantly larger distance from even to the closest cluster, and this is going to indicate and generate a very higher anomaly score. So this is how the k-mean scorer is kind of potentially, using this windowing approach, generate the anomaly score for our anomalies. To evaluate how well our anomaly model works is very simple, and even we can generate right away this plot on the right hand side by calling the show anomalies method with the test data set, actual anomalies, as well as we can assign a certain metric which should be evaluated as part of this method. So basically on the right hand side we see the actual and forecasted signals, and then followed by the norm scorer, which we can see that the score values are quite pronounced around the peaks where the forecasting model fails to capture or be able to predict accurately the ECG signal values, while the K-mean-scorer using the winnowing approach are more able to capture the contextual information, and because of that have assigned a higher score, anomaly score, for where the anomaly actually happens. So when we want to try to binarize these signals, for example a quanti detector, we can instantiate it very simple from the library, defining the quantize below and above we would consider as an anomaly, and assign as part of it both anomaly scores carried as part of this time series object here, and basically we can get both detection and binarization of the signal. We see that the normal scorer with these parameters are performing quite poor, as well as by visually it was quite clear that it's not able to distinguish between the anomalies, while the K-mean-scorer is able to identify with these parameters where the anomaly actually occurred. Obviously this was just for illustration purposes, and extensive hyperparameter tuning and evaluation needs to be created. However, this exercise project with these examples and parameters have been chosen to illustrate that actually the DARTS model of anomaly detection in a very simplistic manner in a few set of lines of code can produce anomaly detection. To conclude, at the beginning of the presentation I illustrated how time series methods play a crucial role in understanding temporal data and how actionable insights can potentially improve it. I hope I also could convince you when it comes to your next time series project that you're going to use DARTS, and providing an extremely user-friendly interface for the time series manipulation, forecasting, and anomaly detection. And I hope I could convince you with this few lines of code exercise that from loading the data to very quickly iteratively explore different models and approaches, next to it right away using Visualize It, the prototyping and the product development, the project development can be fun, very straightforward, and very simple with that. So this presentation was possible thanks to these three gentlemen, especially Julian, who implemented the anomaly model in DARTS, and Dennis, who is actually the lead developer of the open source library, and Samuel, he's a key contributor. So, thank you for watching. See you next time.